everyone, my name is Aniera Larassati and today we're going to do a recap video assignment. So first thing we're going to discuss is what are polymer materials. Polymer is a substance that has molecular structure consisting chiefly or entirely a large number of similar units bonded together. Here are the difference between polymers and other materials such as metals and ceramics. Here you can see the density, weight, plasticity, additive modification, etc. Next one is basic structure of a polymer chain. A polymer chain consists of repeating units called monomers, which are covalently bonded together. These monomers join through polymerization, forming long chains. Monomers are significant because they determine the properties of the polymer, such as strength, flexibility, and chemical resistance. Different combination of monomers lead to polymers with distinct characteristics, making them essential for a wide range of application in various industries, including plastics, textile, and biomedical materials. You can see the polymerization of monomers to polymers chain together. Next one is properties of polymers change with varying chain lengths and branching. From chain lengths, longer polymer chains typically result in stronger materials due to increased entanglement and entropic effect. Longer chains also tend to have higher viscosity and greater resistance to deformation. Shorter chains may exhibit lower strength and viscosity but can have increased flexibility and processability. For branching in polymer chains can affect properties such as crystallinity, density, and mechanical strength. Highly branched polymers often have lower melting points and reduced crystallinity compared to linear polymers, leading to softer and more flexible material. Branching can also enhance solubility and processability by disrupting packing arrangements in the polymer matrix. How are polymers classified based on their sources? They classify in three sources: a natural polymer, which derive from natural sources such as plants, animals, and microorganisms. An example is wool. For synthetic polymer derived from petrochemicals, the example is polyethylene. And the last one is semi-synthetic polymers, derived from natural polymers but are chemically modified to enhance new properties or introduce new functionalities. The example of this is a cast of a plastic bag. The next one is common applications of polymer materials. Polymer materials find extensive use in everyday life due to their versatility, durability, and cost effectiveness. The first one is plastic. Plastic are ubiquitous in packaging materials, household items, and consumer goods due to their lightweight nature, moldability, and resistant to corrosion. Second one is textile. Synthetic polymers such as polyester, nylon, and acrylic are widely used in textile. These materials offer durability, wrinkle resistance, moisture wicking, and dyeability. Last one is medical device. Polymer materials are essential in medical devices and implants due to their biocompatibility, flexibility, and sterilizability. Polymers like PE, silicone, and polyurethane are used in catheters, prosthetics, surgical implants, and drug delivery systems. The next one is thermoplastic elastomers and thermosetting polymers. Thermoplastic polymers soften when heated and solidify when cooled, allowing them to be melted, reshaped, and recycled multiple times without undergoing chemical changes. The example of thermoplastics is polyethylene, polypropylene, polyphenol chloride, and polystyrene. The next one is elastomers. Elastomers are polymers that exhibit elastic behavior, meaning they can deform under stress and return to their original shape when the stress is removed. The example of elastomers is natural rubber, styrene butadiene rubber (SPR), polyurethane elastomers, and silicone rubber. The last one is thermosetting polymers. Thermosetting polymers undergo irreversible chemical cross-linking reactions when heated, forming a network structure that cannot be reshaped or melted upon cooling. The example of thermosetting polymers is resins. The next one is what are copolymers. Copolymers are polymers composed of two or more different polymers units covalently bonded together in a polymer chain. These monomers can be arranged in various patterns within the chain, such as alternating, random, block, or graph configurations, depending on the polymerization process. Here you can see the difference between homopolymers and copolymers. The polymers from the homopolymers, the polymers formed by only one type of monomers, and in the copolymers is from more than one type of monomers. While the homopolymers form the of addition polymerization, and copolymers are formed through condensation polymerization. Here you can see homopolymers consist of single species, while copolymers consist of two or more type of repeating units. Homopolymers have single type of monospecies, and copolymers have two or more types of monomer. Homopolymer often have simple structure, while copolymer have a complex structure. An example of homopolymers is PVC, polyethylene, polypropylene, and polystyrene, etc. The example of copolymer is include nylon 6,6, Dacron, SBRN, etc. Next one is why is molecular weight important in understanding polymer properties? Molecular weight is crucial understanding polymer properties due to its significant influence on various physical, mechanical, and processing characteristics of polymers. From strength and toughness, high molecular weight generally increase the strength and toughness of material, while lower molecular weight polymers tend to flow more easily. From chemical and impact resistance, high molecular weight also enhances chemical and impact resistance of the material. And the entanglement, higher molecular weight leads to increased entanglement of polymer chains, allowing the material to withstand greater stress before breaking. Next one is describe the difference between number average and weight average molecular weight. Number average molecular weight is the mole of fraction of molecules in a polymer samples. Here you can see the equation, and the value is always lesser than weight average molecular weight. By using determination by using gel permeation, chromatography, viscometry, and qualitative methods such as paper pressure osmometry. For weight average molecular weight is the weight fraction of molecules in the polymer samples. You can see the equation. The value always greater than number average molecular weight. Determination by using static light, scattering, small angle, neutron scattering, X-ray scattering, and sedimentation with velocity. Next one is concept of crystallinity in polymers. Crystallinity in polymers refers to the degree which polymer chains are organized in regular order arrangement, known as crystalline structure. Degree of crystallinity indicates the proportion of ordered regions to disordered amorphous regions, typically ranging from 10% to 80%. For properties, crystalline polymers is denser, stronger, stiffer, and more heat-resistant but more brittle. For amorphous polymers, more flexible and easier to process but may lack strength and heat resistance, while semi-crystalline polymers balance between crystalline and amorphous properties. For assessment method, the technique used include density measurement, the SCXRD, infrared spectroscopy, NMR, and microscopy. For the last one is concept of spherulite. A spherulite is a microscopic structure that forms in semicrystalline polymers during the solidification process. The properties they offer a mix of high crystallinity, density, hardness, and brittleness, along with elasticity and impact resistance. For this formation, spherulites grow radially from nucleation sites influenced by polymer structure, cooling rate, and additives. For optical effects, large spherulites exhibit birefringence, creating colorful patterns on the polarized light. Impact on properties. Spherulite formation enhances crystallinity, density, and mechanical properties like tensile strength and Young's modulus. For mechanical behavior, small spherulites often improve toughness and impact resistance in polymers. Thank you for watching. Bye-bye.